spreads out, and it will be related to that, all right? But you'll see. Okay, so the next step is, so what we're going to do is, again, we want to go from here, we're going to take this stuff and plug it into here, all right? And instead of, we want to change variables. Instead of integrating over k, all right, well, we want to integrate over k's from k0, right? Because now, so the whole idea is what I'm saying. A Taylor series works by knowing everything about a function at a particular point, right? So what we want to do is shift this whole problem to saying, look, we know for a real classical particle, it will have a momentum right here. So we want to shift the problem as integrating from momentums about that point. Okay, so we're going to shift variables from k to k's about k0. A lot of words here. All right? And so what he does is he defines the new variable s, and s is defined as k minus k naught. All right? And over here, you know, I could write this. This is omega of k0 plus d omega dk evaluated at k naught times k minus k naught. That might be nicer, right? So what is omega naught defined as? D omega dk defined at k naught? Okay. Okay. Okay, so I'll let you guys do this, all right? But what I did is when I did this, I said, okay, I'm going to find new variables s, and instead of integrating over dk, what am I going to integrate over? ds. All right, so if I'm going to change my variables from dk to ds, what do I have to figure out? What ds is, right, in terms of k. So you go ds dk equals, so ds dk, so I'm changing variables. So look, if I'm changing variables, the first thing I actually do is I change my limits, right? When I'm changing the variables of an integral, I change my limits.
K minus k0, k plus.
Okay, but my limits on the original k were minus infinity, minus k0. So what is that going to be? Minus infinity. And what's the upper limit going to be?
Positive infinity.
Plus infinity. Okay, these are the things that, you know, you do in calculus, but now we're doing real problems, and all of a sudden you got to think about it. All right, and then I got to figure out what dk and ds are. So I'm going to take ds dk, and what does ds dk equal?
K minus k0 dx, or ds is not that.
ds dk equals, tell me. I'm not going anywhere. I'm going to cry, as a matter of fact.
Should be 1.
K is not a constant.
Thank you, Eric. It equals 1. Not that it should be, it is.
Oh yeah, right, case constant, so yeah, it's 1.
It's 1. You guys shouldn't, okay, good. Equals 1, so ds equals dk. Right, so now can I go in and substitute that new variable with the original integral? Okay. Okay, good. So guys, here's all I'm doing. I'm just telling you and leaving out every step that Griffiths does. And this is what you guys should be doing throughout the whole block. And in this case, it was a little bit confusing. So I'm doing it. All right? So when you do that, you get psi of x and t is approximately, why am I going to say approximately?
Because you don't know exactly.
Yeah, that's right.
And,
Because I'm truncating my Taylor series expansion. So no longer can I say equals. I'm only going to use a truncated expansion. Okay? So when you do that, you get it's approximately 1 over the square root of 2 pi times the integral from minus infinity to plus infinity of psi of k0 plus s. So I'm changing my variables, right? So k equals k0, and so k equals s plus k0. Completely changing my variables, and now it's going to be e to the I k0 plus s times x minus guys, you know you're getting old, right? When you start to have your whole books over here. See, it's going to be omega naught plus omega naught prime times s times t, and then integrate over what now? Ds, good. Okay. Now, look at two cases. Look, at time equals 0, you're going to have psi of x t equals 0, and that's going to equal 1 over the square root of 2 pi times integral from minus infinity to plus infinity of psi of k0 plus s e to the I k0 plus s times x ds. All right, and then here's the one I got messed up on. And at some time t, all right, at later times, at t greater than 0, you're going to have psi of x and comma t. Oh, this has to be approximately, right? Because it's an approximately. It's approximately, okay, it's approximately 1 over the square root of 2 pi e to the I minus omega naught t plus k0 omega naught prime t times the integral from minus infinity to plus infinity, minus infinity to plus infinity of psi of k0 plus s e to the I k0 plus s times x minus omega naught prime t ds. Okay, now, this was not at all obvious to me, all right? And so, look at all the omega naughts and everything that we have here. It certainly does not look like this. Right? It's different. And so I couldn't figure out how we did it. And so what I ended up doing is I ended up multiplying all these exponentials together and then looking at everything in the power. And when you look at it, everything cancels out and you end up getting this. Alright? So I had to multiply it out to prove myself that this is just, essentially it's just factoring this. It is not obvious, you won't see it until you multiply it out yourself.
Where'd you multiply them?
So what I did is I said, oh God, I'm going to multiply all these k0s times x's and that.
You just multiplied out the exponent.
Yeah, I multiplied out the exponents and I was able to show that indeed it was that thing. Okay? Okay. So, if you look at this, all right, you can say this equals x of t is approximately equal to, okay, you ready? It's equal to e to the minus I omega naught minus k naught omega naught prime t times, you ready? Compare this to this. Alright, and what's the only difference?
It's good. X minus omega naught t.
So the only thing is the x part, right? The x is x minus omega naught t. Right?
Velocity.
You got it. Alright? So that is times, I could rewrite this part as psi, you ready? Comma, t equals 0. But what would x be? It would be
Minus
x minus omega naught prime t. Okay? Everybody okay? That's the only difference there?
Yep.
Now, here's the key step, guys. Here's what our wave function equals, this thing, right? Now, if I square this thing, so I go psi star psi, what happens to this stuff?
Goes to 1.
That goes to 1. Right? So this is just what we call a phase. Essentially, e to the I something is an angle. It's putting in an angle. It's a phase angle. All right, but what do you recognize a function of x minus omega naught t as? What did we talk about this before? What are all functions? So I'm going to erase this now.
Plane wave.
Okay, it might not be a plane wave, but it is definitely not a standing wave. So in essence, we end up with psi of x comma t is approximately equal to a phase, and the phase goes away, times a function of x minus omega naught prime t, and that thing looks just like a function of x minus vt. And what is a function of x minus vt?
That's a classical.
Classical
Traveling wave.
traveling wave. So this then equals a classical traveling wave with velocity v, right? And what does v equal in this case?
Omega naught prime.
So here, v equals omega naught prime. Okay, and omega naught prime equals d omega dk, evaluated at k0. K equals this thing. This equals d by dk, evaluated at k0 of omega, which is h bar k squared over 2m. So what does that equal?
H bar k over m.
That equals h bar k over m. And does anybody recognize that?
That's the original.
That's the original classical velocity. So this is the original classical velocity. And that's called the group velocity. And again, the group velocity, it equals the classical velocity. Remember, the quantum velocity, the phase velocity, is a factor 2 here. Right? So what did we recover from this whole argument for our real particles represented by wave packets?
We get the original velocity and the normalized.
Okay, and the big picture is the group velocity of that wave packet is exactly the classical particle velocity that we wanted to see. So like David, you're saying, I see you're wrapping up on a bigger level. So now we found a wave packet that's now normalizable and it has all the velocity of our original. Yeah. Cool, huh? This is tough stuff, guys. If you guys can handle this, you're going to go a long way. And you guys can. So if you guys cannot handle the ideas of the Fourier series and the Fourier integrals and the stuff we're doing here, that's as good as it gets. When you do field theory, quantum field theory, you essentially start with these ideas. You start with Fourier integrals. And so that's field theory. Relativistic quantum field theories, you start with the Fourier integrals. All right, so if you guys get the ideas here, you're going a long way. And then plus all these ideas are everywhere in engineering.
How is that similar to path integrals and Feynman's formulation?
Well, that's a little bit different look of formulation, all right, but it ends up with all the same results, all right. So I have never done path integrals from get-go. The only thing I've done of path integrals are Feynman's book, QED, The Strange Theory of Light and Matter. Do you have that book? But it's $12, right? And it's called QED, The Strange Theory of Light and Matter. And it essentially describes path intervals for anybody to understand. And it's the one book written that anybody can understand.